Welcome to G Fun Facts Online. Have you ever looked at a picture of the Roman Colosseum or the Pantheon and just wondered, how are they still standing? These structures are 2,000 years old. They've survived earthquakes, weathering, and the collapse of an entire empire. Meanwhile, a modern concrete bridge or building can start showing serious signs of decay after just 50 years. For centuries, this incredible durability was one of ancient history's greatest mysteries. But what if I told you the secret isn't just a lost recipe, but a technology so advanced it can heal itself? And what if that ancient secret is now inspiring a revolutionary new material that could solve our modern infrastructure crisis? Today we're bridging the gap between ancient Rome and 21st century science to uncover the secrets of self-healing concrete. For the longest time, the hero of Roman concrete was thought to be a special ingredient called pozzolanic ash. This volcanic material, from near modern-day Naples, was shipped all across the Roman Empire. And it was good stuff, no doubt. But it wasn't the whole story. When scientists looked closer at samples of ancient Roman concrete, they found something strange. Little white millimeter-sized chunks were embedded everywhere. For years, experts dismissed these lime clasts as a sign of lazy work, sloppy mixing, or bad ingredients. But that explanation never sat right with researchers like Admir Masick from MIT. He wondered, why would the Romans, masters of engineering with recipes perfected over centuries, be so careless with the final product? That single question led a team from MIT, Harvard, and labs in Europe to a discovery that rewrites the history books. They found that these lime clasts weren't a mistake. They were a feature, not a bug. The key, they believe, was a process called hot mixing. Instead of using slaked lime, which is lime mixed with water beforehand, the Romans likely threw in a more reactive form called quicklime directly into the mix. When you add water to quicklime, you get a powerful chemical reaction, an exothermic reaction, that heats the entire concrete mixture to extreme temperatures. This intense heat did two amazing things. First, it created unique chemical compounds that made the concrete significantly stronger than modern versions. Second, it drastically reduced the curing time, allowing the Romans to build their massive structures much faster. But the most brilliant part was the role of those little white chunks, the lime clasts. They were the leftover bits of quicklime, and they formed a brilliantly integrated automatic repair system. You see, concrete by its nature eventually cracks under stress. In modern concrete, that's the beginning of the end. But in Roman concrete, when a tiny crack started to form, it would naturally spread towards one of these brittle lime clasts. The crack would break the clast open. Then, when rainwater or moisture inevitably seeped into that crack, it would reactivate the highly reactive lime. This created a calcium-rich solution that would flow through the crack, and then, as it dried, it would recrystallize as calcium carbonate, effectively limestone. It would stitch the crack shut from the inside, stopping it from spreading and healing the structure. It's an automatic, built-in healing mechanism. To prove this wasn't just a theory, the research team made their own batches of hot-mixed, Roman-style concrete. They deliberately cracked the samples, then ran water through them. Within 2 weeks, the cracks had completely healed themselves. In some cases, like in seawalls or harbors, this effect was even more pronounced. Seawater filtering through the concrete would react with the pozzolanic ash to form new, even stronger minerals, reinforcing the structure over time. So, while modern concrete is designed to be inert and separate from its environment, Roman concrete was designed to interact with it, and in doing so, grow stronger over time. This brings us to the big problem today. Concrete is the single most used man-made material on Earth. Our cities, our roads, our bridges, they're all built on a foundation of concrete. But it has a fatal flaw. It cracks. These cracks, caused by stress, weather, or just natural expansion and contraction, create highways for water and chemicals to get inside. This moisture then reaches the steel rebar that reinforces most modern structures. The steel rusts, expands, and creates even more cracks, leading to a vicious cycle of decay that ends in structural failure. The cost is astronomical. Just maintaining bridges, tunnels, and retaining walls in the European Union costs an estimated 4 to 6 billion euros every single year. And that's before we even talk about the environmental impact. The production of cement, the key ingredient in concrete, is responsible for up to 11% of the entire world's carbon emissions. Every time we have to repair or replace a crumbling structure, we're churning out more CO2, fueling this destructive cycle. We needed a better way. And inspired by the genius of the Romans and the self-healing properties found in nature, scientists have developed one, bioconcrete. This isn't just an improvement, it's a paradigm shift. Bioconcrete is, in a very real sense, alive. The concept was pioneered by Dutch microbiologist Hendrik Jonkers back in 2006. After years of testing, he found a way to embed dormant bacteria into the concrete mix. He chose specific strains, usually from the Bacillus genus, because they are incredibly tough and can survive the highly alkaline, hostile environment inside concrete. Here's how it works. Along with the bacteria, tiny biodegradable plastic capsules containing a food source, usually calcium lactate, are added to the concrete mix. As long as the concrete is solid, the bacteria remain dormant, like seeds waiting for spring. They can stay viable like this for up to 200 years. But the moment a crack forms and water gets in, the magic begins. The water dissolves the biodegradable capsules, releasing the food. This wakes up the bacteria. They begin to eat the calcium lactate, and through their metabolic process, they precipitate calcium carbonate. In other words, they excrete limestone. This limestone fills the crack, sealing it off from any more water and preventing the corrosion of the steel reinforcement inside. The structure literally heals itself, using microscopic masons that spring to life exactly when and where they're needed. The science behind this is a process called microbially induced calcite precipitation, or MICP. The bacteria are chosen because they can form protective endospores, allowing them to survive the violent mixing process and then lie dormant. When activated by water, their metabolism produces carbonate ions. These ions grab onto calcium ions already present in the concrete, and together they form calcium carbonate crystals. These crystals grow and expand, locking together and filling the void. There's even a bonus benefit. During this process, the bacteria consume oxygen. Less oxygen inside the concrete means much lower risk of the steel rebar corroding, adding another layer of protection. And don't worry, the bacteria used are completely harmless to humans and can only survive within the specific chemistry of the concrete. This technology isn't just stuck in the lab, either. It's already being tested in the real world. Researchers have developed not just self-healing concrete, but also a repair mortar and even a liquid spray that can be applied to existing structures to give them self-healing properties. A dedicated building in the Netherlands is undergoing long-term endurance tests with the goal of bringing these products to the commercial market. This innovation is part of a wider, exciting field called biofabrication. For example, a company called Biomason is using bacteria to grow bricks. They mix loose sand and aggregate with bacteria, which then cement the particles together, similar to how coral reefs form. This process creates bricks that are just as strong as traditional ones, but with a fraction of the carbon footprint. In another stunning example, an installation in New York called the Hi-Fi Tower was built from 10,000 of compostable bricks grown from mycelium, the root network of fungi. The project proved that we can use biological materials for structural purposes, and at the end of its life, the entire structure could be composted, leaving almost no waste. Now, of course, bioconcrete isn't a perfect solution just yet. The biggest hurdle right now is cost. The bacteria and their encapsulated food source make bioconcrete more expensive upfront than the traditional kind. But researchers are working on it, exploring cheaper nutrients like sugar-based formulas. And when you factor in the massive long-term savings on maintenance and repairs over the decades-long lifespan of a structure, that initial investment starts to look a lot more attractive. The other challenge is gathering more long-term data on how bioconcrete performs in all sorts of different climates and conditions over many decades. Lab tests are promising, but nothing beats real-world evidence. What we're seeing is a beautiful, full-circle moment in human engineering. We've unlocked the wisdom of the ancient Romans, understood the elegant chemistry that allowed their creations to endure for millennia, and translated it into a cutting-edge, biological technology for the 21st century. Bioconcrete offers a future where our infrastructure is more durable, requires far less maintenance, and has a much smaller carbon footprint. It's a move towards a world built not just with brute strength, but with intelligent, living materials. The journey from the hot mixed concrete of the Colosseum to the living concrete of tomorrow is a powerful reminder that sometimes, to build the future, we have to start by looking to the past. Thanks for joining us on Fun Facts Online.